Section: Introduction. In this section, we will discuss the basics of conditional generative models, CGMs, and explain in context learning, ICL, from our perspective. We will define hallucinations and hallucination rates, and then demonstrate how to estimate the hallucination rate given an ICL problem and a CGM. A conditional generative model, CGM, is a type of sequential model where certain parameters define the model, and elements determine the distribution. When the conditional distribution operates over linguistic units and the parameter size is large, these models are known as large language models, LLMs. Although we will focus on LLMs, our methods can be applied to various conditional generative models. These models are commonly implemented using transformers, which are sequential neural network architectures. In an in-context learning, ICL, problem, we have a tuple consisting of a model, a dataset, and a query. The dataset, also known as the context, comprises a sequence of examples. When presented with a new query, the model uses the query and context to generate a response. One way to view ICL is through a Bayesian perspective, linking it to Bayesian statistics. This viewpoint assumes a joint distribution over all query and response pairs. It suggests that this distribution can be represented with a latent mechanism determining the task being performed. Additionally, we assume that the pre-trained language model approximates the posterior predictive distribution under this joint distribution. ICL with an LLM can then be seen as a form of implicit Bayesian inference. By adopting this approach, we can construct and estimate a posterior hallucination rate, which indicates the probability of a generated response from the model being in an unlikely region according to the true, latent mechanism. We will establish our notation and terminology, including defining mechanisms, query response pairs, random variables, and distributions, to facilitate our discussion on estimating the posterior hallucination rate. Section Summary. In this section, we introduce the concept of estimating the hallucination rate for in-context learning, ICL, using a conditional generative model, CGM. By taking a Bayesian perspective, we can define the posterior hallucination rate, PHR, to estimate the probability of generating errors, or hallucinations, in response to a given query within an ICL problem. Our method involves sampling from the predictive distribution of the CGM to compute the PHR, which can provide accurate estimates of the empirical error rate in natural language ICL problems. Section: Hallucinations and the posterior hallucination rate. In this section, we define hallucinations and the hallucination rate using the concepts of CGMs and ICL. We start by considering a scenario where we observe a true mechanism 45, number 45. To determine which values of 31, number 31 could be considered hallucinations for a query 23, number 23, we define a 1 to 47, number 47, likely set of 48, number 48 and 49, number 49 as any set 50, number 50 satisfying 51, number 51. Then, for fixed 1 to 5, number 5, likely sets 52, number 52, a value 31, number 31 is labeled a hallucination with respect to 23, number 23 and 29, number 29 if 53, number 53. For instance, if the true generative model of 25, number 25 is a Bayesian linear model with known parameters, we can set a likely interval based on the model's distribution and identify values outside this interval as hallucinations. When making predictions without observing the true mechanism 45, number 45, we determine the true hallucination rate, THR, as the probability of sampling a hallucination given the true mechanism and query. The THR is higher when the predictive model assigns high probability to unlikely regions and lower when it focuses on likely areas. Although we cannot directly observe the true mechanism 45, number 45, the dataset provides evidence through the posterior distribution 67, number 67. We introduce the posterior hallucination rate, PHR, as the probability that a value 31, number 31 falls outside the high probability interval of 29, number 29 and 23, number 23 when sampling. The PHR helps quantify the likelihood of hallucinations in linear regression scenarios. To calculate the PHR from predictive distributions, we leverage Dub's theorem to transform statements about the predictive distribution into statements about the response variable. This allows us to compute the PHR without direct access to the true mechanism distribution. By using a finite approximation, we can express the true and posterior hallucination rates in terms of finite sequences, avoiding the need for a distribution on the query variable. Section Summary. In this section, we define hallucinations and the hallucination rate using the concepts of conditional generative models, CGMs, and inverse causal learning, ICL. Hallucinations are values that are unlikely to be generated from the true mechanism, and we introduce the true hallucination rate, THR, as the probability of sampling a hallucination given the true mechanism and query. Additionally, we define the posterior hallucination rate, PHR, as the probability that a value will fall outside the high probability interval of the posterior predictive distribution when sampling. Section. Estimators for the posterior hallucination rate with CGMs. In this section, we develop estimators for the posterior hallucination rate using CGMs. We introduce an estimator for a specific equation by replacing certain values and utilizing Monte Carlo estimates for integrals and quantiles. Our algorithm, predictive resampling for hallucination rate estimation, calculates the outer integral in the equation. Within this algorithm, a subroutine estimates another equation. In the context of a CGM, predictive resampling can be easily understood without relying on Bayesian statistics. Initially, we generate new query response pairs based on the model's predictions. This process can be likened to asking the model to predict future pairs it will encounter. Subsequently, we generate a new response and assess its coherence with the given task. If the model is confident about the task, the pair will align well. However, if the model is uncertain, the response may not match the task. In practical scenarios, response lengths can vary, so we average the likelihood calculations over the response length. For more detailed assumptions supporting our method, refer to the appendix on assumptions. We then evaluate the accuracy and usefulness of the posterior hallucination rate, PHR, estimator through empirical analysis. Initially, we test whether the PHR estimator can predict the true hallucination rate, THR, accurately. We conduct synthetic regression experiments to calculate the THR and observe that the PHR reliably predicts the THR for certain tasks, showing robustness across different parameter values. Additionally, we find that the PHR estimator performs better for smaller dataset sizes. Moving on to natural language tasks using large language models, LLMs, we assess the PHR estimator's ability to predict the model's hallucination rate and empirical error rate. The PHR estimator consistently predicts the model's hallucination rate and remains robust across various dataset sizes and parameter settings. Moreover, it accurately forecasts the empirical error rate for specific parameter values. The estimator's accuracy is influenced by the LLM's performance on the task, improving as the number of examples increases. In synthetic regression tasks, we compare the PHR estimates with the true hallucination rate, THR, in a controlled setting where we know the underlying mechanism. We modify the Llama 2 architecture to model sequences of continuous variables and generate datasets for training and testing. The results show that the PHR closely aligns with the true hallucination rate, although it tends to underestimate it, especially with an increasing number of examples. We investigate potential sources of underestimation, such as distributional discrepancies and model limitations, suggesting avenues for improving predictive accuracy in CGMs. Section Summary. In this section, we introduce estimators for the posterior hallucination rate within conditional generative models, CGMs. We develop an estimator that replaces certain components and leverages Monte Carlo estimates for integrals and quantiles. Through empirical evaluation, we demonstrate the reliability and robustness of the posterior hallucination rate, PHR, estimator in predicting the true hallucination rate, THR, across different dataset sizes and settings, showcasing its effectiveness in various scenarios, including synthetic regression tasks and natural language tasks using large language models. Section: Natural language tasks. In this section, we evaluate the performance of the posterior hallucination rate estimator on various natural language tasks using the Llama 2 family of models. Since we do not have access to the true answers in this scenario, we introduce a new metric called Model Hallucination Probability, MPH, to compare against the hallucination rate. We also compare it with the empirical error rate based on the correct responses. We focus on tasks from 6 datasets: Stanford Sentiment Treebank, SST2, Subjectivity, AG News, Medical QP, RTE, and WNLI. We filter out queries longer than 116 tokens. To implement in-context learning for each dataset, we create a balanced training set of query-response pairs and generate responses from the Llama 2 model. We structure the input by adding specific strings. The model's performance varies across tasks, with better results for some tasks, in capability, and poorer results for others, out of capability. Assessing the accuracy of the posterior hallucination rate on LLM tasks is challenging due to the lack of true answers and limited response samples. We introduce the model hallucination rate, MHR, as a complementary metric, assuming the model's posterior is correct. The MHR estimates the probability of hallucination when additional ground truth examples are included. We compare the posterior hallucination rate with the MHR to evaluate its performance across different tasks and context lengths. Our results focus on Llama 2 to 7B, where we set specific parameters. The comparison between the posterior hallucination rate and the MHR shows promising results, especially for certain tasks when the parameters are appropriately chosen. However, for tasks where the model struggles, out of capability, the posterior hallucination rate may not accurately reflect the error rate. Further analysis and parameter adjustments are explored in additional results. Section Summary. In this section, we evaluate the posterior hallucination rate estimator on various natural language tasks using Llama 2 models. We introduce a new metric called Model Hallucination Probability, MHP, to assess the estimator's performance against empirical error rates. By comparing the posterior hallucination rate with the MHP, we aim to determine its effectiveness in differentiating between in-capability and out-of-capability tasks based on the model's predictive distribution. Section: Discussion. In this section, we have introduced a novel approach to predict the rate of hallucination in context learning using conditional generative models. We have provided a theoretical rationale for our method and demonstrated its accuracy in estimating the probability of hallucination through synthetic experiments. By leveraging pre-trained language models, we have shown the utility of our method in forecasting error rates in natural language tasks involving in-context learning. However, precise estimation of the hallucination rate relies on 2 key assumptions. First, that the data for in-context learning can be represented using De Finetti's theorem, and second, that the conditional generative model accurately reflects the true distribution. Our results support these assumptions, but we have also observed that even slight discrepancies between the model and the true distribution can lead to underestimation. Furthermore, we have identified cases where the predictive distribution of a pre-trained language model deviates significantly from the true Bayesian posterior predictive distribution in synthetic in-context learning tasks. These discrepancies pose a challenge in using the hallucination rate as a decision-making tool, emphasizing the need for future research to enhance the robustness of the estimation method or optimize conditional generative models for in-context learning. We would like to express our gratitude to the individuals who contributed to this work through their reviews, feedback, and support.